In this lecture, I'm going to talk about the analysis of variance. So here, the analysis of variance is very important in the experimental design. Typically, when we compare the different means, so here I'm going to talk about the one-way ANOVA, which is widely used to compare the k-sample means, and then two-way ANOVA when we have the two factors and we are interested in the associated corresponding interaction of the two factors. So this analysis of variance is the, as I said, widely used experimental design. So when you have the factor, which is the kind of a predictor variable in the linear regression, and these factors are usually the categorical variables, and then they have the labels, which is the sub-level, label is and of the category, which is the sub-part of the categorical variable. For example, if you have the drug, then you have the treatment giving, say, 20 doses and 40 doses and 60 doses. Then this treatment is your factor, and then doses are your labels. So by using this analysis of variance, you can evaluate the, for example, for one ANOVA, you can evaluate the effects of the factors. And especially this is experimental design, then you can build up the causality on here. Two-way ANOVA is useful when you have more than the two factors. More than one factor. So here, one-way ANOVA is equivalent to comparing the k-sample means. So we have only one factor, and then if we have the more than the one labels, then it is just comparing the means of the different population. So before talking about one-way ANOVA, let's talk about the review the two sample means. So for two sample means, we already talked about it before. So we can first do the summary statistics. You can use a proc means and proc univariate for each group. So in this example, we would like to compare the means of the shoe size between those index fingers are longer and those ringer fingers are longer. So we can use proc means. So in this case, we actually this long thing has three levels. Ring, same, index. So ring is the ring fingers is longer. Index means index fingers longer. Same is both are the same. So we use a where statement to only pick up the group of ring and index group levels. So in this case, we use a proc mean procedure. We can get each mean within the group of index and ring and standard deviation and minimum and maximum. And we can create a side-by-side box plot. So we can use the first short part long thing, and then make a plot by shoe size times long thing. So we can use a box plot procedure. And then we can use independent two-sample t-test because we can think that the long thing group and then the ring group and the index group, they are two independent population, and so no hypothesis that two independent groups have same mean. So they are two independent groups, so that we can use two-sample t-test based on the normality assumption. And And then so we are looking at looking at the shoe size. So shoe size is our dependent variable. Then we are looking at the variable this long thing on here. And then we can see that, so as I said before, there are three components in this two independent group t-test. First one is the descriptive statistic for index for long thing in this case. And then second one is the mean and 95% confidence limit of the mean and standard deviation, and 95% confidence limit for standard deviation. And then we can have the difference based on the pooled method, Satterwhite method here. So in the pooled method, we consider that their population values are equal. Satterwhite method, that considers that their population values are different. So before looking at this third part, the test, as I said before, we need to look at the equality of variance test. So equality of variance test, so it's the p-value is greater than 0.05. So the null hypothesis here is the two population variances are equal. Alternative hypothesis that these two population variances are not equal. And then so here we do not reject null hypothesis, which means that the two population variances are equal. So we need to use this pooled method. So we can get degrees of freedom and the t statistic, and this is less than 0.05. So we can conclude that the shoe size between two groups are significantly different. And then if normality assumptions that are not satisfied, you can use the Wilcoxon rank sum test, which is alternative of the two sample t-test. You can use that, and you can also get the same result as t-test. So please try to run this code by yourself. So here, when we have more than two groups, so we can, so here we still have the one factor. So we have one factor, and then it has the more than two levels. Then we have more than two groups in here. Then in that case, t-test and Wilcoxon rank sum test do not work. So then in this case, we can use the analysis of the variance to test whether the differences means the statistical significance. So here we use the analysis of variance. So here the reason why I use a variance to analysis in the analysis is that, so this variance explains the variation due to the different sources. And then in this case, so we have a variable, and it is partitioned into the parts attributable to a different source of variation. So if your variable is as a linear regression explains the variability, most of variability of the change in your responses, then it is you can think that this is significant. It means that your differences between the groups or levels, difference of the means of responses in the levels, they are the significant. So here in this example, we use all three different groups: long index finger, long ring finger, and the same. And then the null hypothesis is that mu1 equal to mu2 equal to mu3, and then alternative hypothesis is the each pair of them is not equal. So here the one thing I have to mention about this alternative hypothesis that they are not equal each other. At least one of them is not equal. So here the null hypothesis that they are all the same, but the alternative hypothesis that they are pair of them, at least one pair of them is not equal. So the alternative hypothesis can be mu1 is not equal to mu2, but mu2 may be equal to mu3 and mu1 may be equal to 3. So if at least one pair is not equal, then that's sufficient for the alternative hypothesis. Of course, alternative hypothesis includes that all series are not equal. But here, formally, the alternative hypothesis is that at least one pair of them is not equal. And then I recommend using proc GLM for Anova in SAS because proc Anova is not able to create the contrast maybe needed in the follow-up analysis. For contrast, I will explain about it later. So the proc GLM, the form is proc GLM data equal data. Then we use the class variables, which is the variable that divides data into groups. And the model statement, which is a dependent variable equal to independent variable. So it's a response variable equal to the variable that is used as the predictor. So use the proc GLM. So we have a class as long thing because the long thing is the main variable, main independent variable, and the model equal to shoe size equal to long thing. So long thing is the main independent variable. And then this is one-way ANOVA. And then you can see that there is a one-way ANOVA table. So here is the one-way ANOVA results. So this F value is the 60.66 and P value is less than 0.001. And then we have the R square. And then we have a type 1 sum of square and type 3 sum of square. So this type 1 and type 3 in this one ANOVA, it doesn't quite matter. So I mean, it matters when you have more than the one variable. So I will not explain about details right here. So the sum of, it's the same as the sum of squares on here. It should be, and because we only have one variable. And then we have R squared, this is quite low. And then you can see that this is the, so this is F value, and the P value is the test for mu1 equal to mu2 equal to mu3. And then here is the less than 0.05, so we can say that there exists the a difference and at least one pair of the means. So, or the means of the shoe size across the left variable long thing are significantly different. So if one-way ANOVA shows difference, and as I said, this one only tells about at least one pair of them is different. So we don't know which pair is different or not. So to do a more analysis, then in here we have the comparing mu1 equal to mu2 and mu2 equal to mu3 and mu1 equal to mu3. Then it causes the multiple comparisons of the population means in different groups. So that, and then but there should be adjustment for this multiple comparisons because it blows the type 1 error up. So I mean, I will not talk about details in the multiple comparisons on here, but for this you can understand that due to what we compared to the population mean several times, so we have to do a multiple testing, so it makes the type 1 error go up. So we need to use the multiple comparison procedure, so which is the Bonferroni t-test and the Schufest and multiple comparison test and Tukey's student times range test. For these details, I'm not gonna talk about these details in here, but for these details, please Google them. So we can use the means statement and the variable, and then slash with specifying the option. So we use a Born-Ferry t-test on here. Then we can get the output on here. Then due to Born-Ferry's t-test, we observe that the difference between ring and index is the only significant on here. So based on the analysis of variance, we confirm that there is at least one pair of means is different. And then for this multiple comparisons, which is a follow-up analysis from the 1A Anova, then we confirm that the ring and index groups are significantly different, but the other comparison says same and ring group and the same index group, these differences are not significant. So then the next one is I would like to talk about the contrast. So in many situations, researcher may determine a priority, which means they would be like to compare. So it doesn't have to be multiple comparisons. So here we say in this example, we would like to say okay, so mean of first and second group is equal to mean of third group. So you think that if we take a mean of first and second group, then that's the same as the third group. So that's the scientist researcher may have interest, or you think the difference of the two groups is equal to the mean of the third group. So then this is called the contrast. Then we can specify this contrast by using the contrast statement with the label variable with A1 to A to AK. So AK to AK, they are the coefficients on this means on here. So let us specify the name of we give the contrast. And then these A1 to AK are a set of all the coefficients that make up contrast. So and notice that if you add all of the contrast coefficient, then it should be the 0. So for example, let's say if we have hypothesis that you have the mean of the population mean of same group is equal to the mean of the shoe size means of the other two groups, where the population mean of the shoe size of mean same group is equal to the mean of population mean of the index group and the ring group. So we can submit the code in the contrast statement. So this contrast is we have a contrast, we put the name as same versus as different. And here's the variable that we are interested in is long thing. So we have long thing, and we have a -1, a -0.5, -0.5, and 1, because if you so this same is a third group. So if you move to this left hand side, then this coefficient would be -0.5, and then here for index, and then for coefficient for ring is the -0.5, and then here same group is going to be 1. So that's why we have in order. So this is for the first group. The contrast coefficient is -0.5. Second group, the -0.5, and the third group is the same, so we have only 1 on here. So you can specify the coefficient that the contrast coefficient that way. And then if you look at that, the sum of square is the 0.008, and the f value is the very small. So and the p value is the greater than 0.05. So we cannot reject the null hypothesis and then conclude that the mu equal to same is equal to average of the mu index and mu ring. So which means that the mean of the shoe size in the same group is equal to mean of the shoe size of the index. Mean of the average of the mean of shoe size of the index and the ring. And then for non-parametric test, if you have small sample size and then have you think that it is very difficult to satisfy the normality assumption, and then you can use the Kruskal-Wallis test. So Kruskal-Wallis test is using the proc n power 1 way together the Wilcoxon option that generates the Kruskal-Wallis test. So you can use the proc n power 1 way data equal to shoe size 2, and then we can specify the Wilcoxon option. And then other class variable and variable is the same as before. And you can get the sum of the scores and the mean score and the expected scores. And then you can get the Kruskal-Wallis test, and then this p-value is small, so it rejects the null hypothesis, which means that at least one pair of the population means are different. So which is the same conclusion as the one-way Anova. So here in the previous example, we get the association between shoe size and the long fin. However, we cannot conclude the long fin causes to the larger shoe size, which is the scientifically unreasonable. And then here, this study is not the randomized experiment. So we cannot build up causality here. We can only see the association. If we want to draw causality, then we have to have a randomized experiment. For example, if you want to test efficiency of drugs, and we build a randomized experiment, so this randomizer removes the all the effects that might affect the on the responses. So it guarantees that all other factors are same for three groups except the drug effect factor, so that the drug effect factor is only one that causes a difference of the responses. And then we can perform one-way Anova in this example, and then we can draw a conclusion about the drug efficiency. So in this case, we can conclude that drug is so if there's a difference, the difference between the three mean outcome of the three several groups, then we can say that drug level changes the difference. So which means that change of drug level causes a difference of your response. If you do not have the randomized experiment, then you cannot say the causality here. Okay, so two-way Anova. So two-way Anova is when we want to compare the mean of populations that are classified two different ways, or you have the two factors in the experiment and with the responses, and then so you have the general syntax of GLM is same as the one-way Anova in this two-way Anova. In this class statement, we have two factors, so we have put the two variables on here. And then the model statement is used to define the format of model. And then here we need to include the interaction term if we want to see interaction between A and B. So we have factor A and factor M, and there may be an interaction between these two. So we have to use A, B, and A star B. If you do not want to specify interaction term, then you can just say A and B on here. And so let's look at the long fin and the gender as two factors. And then we can add the class statement with long fin and gender. And the model is shoe size, long fin, gender, and long fin start gender, or you can use shoe size long fin bar with gender, alternative expression of this line. Then you can see that we can have this model factor, which means that our model is significant, which means that at least one pair due to these two factors is different. And we have R square, and 0.56 is higher than before. And we have two tables on here, so type 1 sum of square and type 3 sum of square. So this is maybe confusing to you. So briefly speaking, type 1 sum of square, that we would consider the order in your model fitting. So here, we calculate sum of square when you first add the long thing. So that's the sum of square. And then after, given that long thing, only long thing, and you compute the sum of square for gender. And then if you compute the sum of square for gender for interaction, then consider given that you have long thing and gender. So this sum of square is a sequential, so this is usually called sequential sum of square. And then type 3 sum of square is you adjust all the effects no matter what the order is. So here you have long thing and sum of square. Then this sum of square is computed in the presence of gender and long thing and gender. So this is the sum of square you get on here. Then gender, so the sum of square for gender, this variability of gender, is computed on the presence of long thing and the long thing and gender. And then long thing and gender interaction is computed from the sum of square is computed on the presence of the long thing and gender. So this sum of square is adjust all the effects of variables for each item. I mean, usually many statistical software we have usually consider type 3 sum of square, because this type 1 sum of square is dependent on the order dependence. If you change your order here, so if gender is first and the long thing is first, then your sum of square is going to be different. And then note that here the sum of square for long thing and gender interaction, they are the same for type 1 and type 3. Type 3 because they are here, they put the last one here, so they have for sum of square 1 and interaction long thing and gender, they have same effect as the sum of square 3 on the long thing and gender. So you can see that for the sum of square for type 3 sum of square, the gender is only significant. There is no interaction effect and there is no main effect on the long thing. So interaction plot is useful to look at whether there is an interaction effect by graphically. So this is a formal test. So you can see that there is no interaction effect by formal test. So this one shows a separate line corresponding means corresponding each level of second factor. So it computes the change of the factor you are interested in, change of the mean by the factor you are interested in by each level of the second factor. So if this is a parallel, means that your second factor does not there's no interaction effect because the second factor does not makes a change in here, or your factor in the x-axis does not make a change. For example, if you have the interaction per shoe size, it does not have any change between this due to the ring size. So we can see that there's no interaction effect, and that this is consistent by this proc-GLM. So this interaction plot is very useful to look at the interaction effect by graphically. And then for formal test, you can use this Anova table. Okay, so I will stop on here, then I will continue in the next video.